I know.
Hello, everyone. Welcome back. I started to grade their assignments, but I'm not quite done. But I'll have that back in the next few days. Even if you want to sit one seat closer there.
That's probably a better idea.
And I do have the in-class assignment ready for today. I haven't made the at-home assignment yet. I just wanted to make sure I understand what happened on the first assignment before I make the next one in case I need to do any adjustments. But that will be ready in the next couple of days, at least the first part of it, based on independent samples t-tests. Because there will be 3 sections to this module: independent samples t-tests, which we might finish today, but we might have to finish next week. Paired samples t-tests or dependent samples t-tests. It will probably be shorter because it's a lot of that will duplicate what we see today. And then the third section would be the advanced t-test section. But the plan so far is today, independent samples t-test, next week, dependent samples t-test for everyone. And then the week after that would be for mandatory for PhD students, the advanced t-test. Any questions about our schedule? Once I grade your assignment, I will send them out to you individually so you can see your grades and feedback and all that. And at that point, if you have questions, let me know. So let's talk about t-tests. And in some ways, t-tests might be simpler than correlation. They're both fairly straightforward. Oh. All right, so typical overview. And before we get into examples, say, okay, well, when do we use a t-test? So a t-test is used when we want to compare 2 groups or 2 conditions. And I've got 2 examples for that. The first is what we're going to talk about this week, and then the second is what we'll talk about next week. So a t-test can assess whether 2 groups / conditions are significantly different. And just like we saw with correlation, that's when alpha is less than or equal to 0.05. That's our typical threshold for significance. Or not significantly different. In other words, alpha greater than 0.05. But no surprises there. So here's the 2 examples. We could have a control group that takes a placebo. So let's say 10 participants. And then we get another 10 participants of different 10 people, and they take L-citrulline. And then we want to compare the arterial function of those 2 groups. So 20 people total, 10 control, 10 L-citrulline. And for that, we need an independent samples t-test. That's what we'll talk about today, because those 2 groups are unrelated or independent from each other. Example 2, I tried to go with examples that we might see in our department. So we want to look at the strength of women who are postmenopausal. And so what we're going to do is we're going to test their strength, let's say 10 women. And then we are going to have those same 10 women take tocotrienol, someone how to pronounce that? I don't know where I came up with that one. I don't know if it was from some of the research here, or if I just Googled how to increase strength. And then we'll test their strength again. So it's the same 10 women tested twice. And that those 2 groups, well, it's not 2 groups, it's 1 group because they're dependent. And for that, we need a paired samples t-test, and that we'll talk more about next week. So what are the trade-offs of these 2? So of course, independent samples, we have the 2 groups. Whereas paired samples t-test, it's the same group participants tested twice. Another way to visualize that, just make sure we're all completely clear about this. For independent samples t-test, you have different participants in the 2 groups. So no one is the same. If there was, that would violate one of the assumptions of an independent samples t-test. Paired samples t-test, there's a few caveats, but typically it's the same participants in both groups. There has to be something that pairs them together. This is the most common way to do it. So let's look at the example from the textbook, at least one of the examples. So it was, does an invisibility cloak affect the number of mischievous acts? Are we all familiar with Harry Potter and invisibility cloaks? Okay, it's still relevant. So I guess, was it, did they just have the 10th anniversary or the 20th anniversary of the film? 20th, wow, okay. And then the books, maybe 30 years ago?
I think 40.
40? Wow.
I was a kid when they came out on 29, so I remember my aunt called it. She's like, I think you really like these. She said it to my brother. I don't really know, but yeah, she really called it.
Yeah, it took off. So we've got two different groups of participants. And one group, we don't give them any invisibility cloaks. So, normal everyday life, they go about, we see how many mischievous acts they commit. And the mean number of acts was 3.75. There were 12 participants in this group, and we have their standard error, standard deviation, their standard error. And from that, we calculate a tolerance. Then we have another group of participants, different 12 participants, and we give them invisibility cloaks, and we see how many mischievous acts they commit, and the mean is higher. The standard deviation is actually lower, so is the standard error, and there's the confidence interval. And we want to know, is there a significant difference? So to do that, we need to run an independent samples t-test. And I think I stepped through it here in the slides, but we'll just do it in SPSS. So here are the data, and we need a coding variable in this case. So the cloak, 0 means they did not wear a cloak, and 1 means they did wear a cloak. And then over here, this is the number of mischievous acts for each participant. I don't see the menus here, but we're want to compare means, and we're going to do an independent samples t-test. And say, okay, well, which variable do you want to look at? Well, we want to look at the number of mischievous acts. And which variable groups your participants? Well, that's our cloak variable. And we actually, in this case, have to tell it what are the two levels of cloak. And it was 0 and 1. So do we need any options here? No, actually, that should be fine. And we'll say, okay. So here we go. Let's switch to PowerPoint for some, we'll just make the output a little larger. So the first part here, it gives us the number of participants, the mean for the two groups, standard deviation, standard error. We saw those on the previous slide. It doesn't give you the confidence interval. You can calculate it, or you can ask SPSS to do it, but in this output, it doesn't give it to you right away. I think it's always good to check, okay, well, we were expecting 12 in each group. Did we see that? And sometimes input goes wrong. We get to SPSS, it drops someone, so it's good to check those numbers. Now here's our statistical results for our independent samples t-test. We'll talk more later about whether we can assume equal variances or not assume equal variances, but for now, we'll just assume equal variances. So this is if you can't assume equal variances. And the critical values for our t-test, well, we want to know, is it significant? That's our p-value. In this case, it's 0.101, which is greater than 0.05, so these two groups are not significant. The other things we report for a t-test is the t-value. We've seen t-values already. We'll talk a little more about that. And then this is the number of degrees freedom for that t-value. Now, in correlations, remember it was like the number of pairs minus 1. Here, it's actually the number of participants. I think I did the math on the screen. The number of participants in one group minus 1 plus the number of participants in the other group minus 1. So in this case, it's 12 minus 1 plus 12 minus 1, so 22. So I guess you can think of it as the total participants minus those are your degrees of freedom. And this is typically how it would be reported. So we give the T, and that's lowercase and italicized. Inside is the number of degrees of freedom. We're going to report our T value to 2 decimal places as is format. Do a little comma. P value also italicized equals, and then we round our P value to 2 decimal places. Are there any questions about basic t-test output? We'll look at everything behind this. So first of all, the logic. We'll kind of look at this at a very basic level, and the advanced class we'll go deeper, and actually we will look at the math behind a t-test, because similar to the correlation math, it's not that complicated, and the t-test math is probably even easier because you don't need to calculate covariance. So with the correlation, remember we had to draw a line in the sand. So okay, well, what is significant? We said if that correlation is more extreme than 95% of correlations on random uncorrelated data, then we'll say that's significant. And that same logic is going to apply here, and is there to most of our parametric statistics. So again, we're going to draw a line in the sand. Okay, let's say we take 2 random sets of data from a from the same distribution, from the same population. So ideally, they would not be significantly different. And if you calculate the mean in one sample, the mean in the other, and you subtract them to calculate the mean difference, most of the time it would be 0. But sometimes, and that's actually what I did here in MATLAB. I used a normal distribution, and I pulled 2 samples of size 12 to be similar to our statistical test we just saw. And then I calculated the means and I subtracted them. And most of the time, you're going to get a mean difference of 0. But every once in a while, one group, randomly by chance, has a slightly larger mean, the other one has a slightly smaller mean. Then when you subtract them, you're going to get either a positive difference or a negative difference, depending on the order of those operations. So this is the distribution of data that we expect, even when you're taking 2 samples from the same population. So what we're going to do is we're going to draw a line in the sand and say, okay, well, if we do a test and the difference we see is in the 5% of this extreme, and that's when we're using alpha of 0.05, we'll say that it is significantly different. So again, 5% of the time we're going to be making a mistake. We're going to be making a false positive. And if this histogram looks familiar, it's because it's a t distribution, and here's the exact t distribution with 22 degrees of freedom. And it's, I don't know how many samples I did here, but maybe a few million. MATLAB can do that quite easily. So you can see that the shape is very, very similar to this t distribution with 22 degrees of freedom. So all we need to do is, using t-tables or ttable.org, is find out, okay, well, what is the t value that gives us 5% of the data in these extremes? So we've got 22 degrees of freedom. We want to find that 5% value. So 2.5% are going to be on each side. So we want to go to the 2 tails contain 5%, or 1 for each tail has 2.5%. And that's our critical t value, 2.074. So at 2.074, 95% of the mean differences are within that bound, and 5% are outside those bounds. So when we run the t-test, we're basically looking, is the t value 2.074 or larger in either a positive or negative direction, because this is a 2-tailed t-test. We'll talk about 1-tailed versus 2-tailed later. And then let's see, what was our, can I come back to the actual value? Oh yes, so there's our t value. Remember, it was negative 1.71. Oh, great, I drew one. So that's right here. That is not in the extreme 5%. And that's why it's not significant. And then with some, using SPSS or that website I showed you, you can ask for the exact p-value related to the t-value that we got. Any questions about the logic behind a t-test? So in this next section, we're talking about the assumptions behind a t-test, and this is partially, we'll review what we saw with correlations, and for the ones that we're reviewing, we'll kind of do them in half the time we did before, and we'll focus on the newer assumptions. So t-test assumptions, because we'll see this next week as well, I've already grouped them into assumptions that are required for independent and paired samples t-tests, and if you notice, those are the same three we saw with correlation. So we already know about them. We'll review them quickly today. Now, only independent samples t-test and not paired samples t-test, the groups have to be independent, and you need to have equal variance between your two groups. And the latter one is what we'll look at in more depth. Let's see. So these three we've already seen. So continuous, the data need to be either interval or ratio. Not a surprise, that's what's required of, I think, all parametric statistics. You can look, outliers, yeah, outliers. The easiest way to look at those are box and whisker plots. The challenge is more, if you have outliers, what should you do? And that typically depends on your area of research and the specific dependent variable. If you want to remind yourself how to do that, you can see the slides to pull up box and whisker plots. In this case, in this made up data, there were no outliers. So what do we do if there are outliers? Well, as I said before, if you made a mistake in data entry, fix it, that's fine, that's great. If there are outliers, you can rely on robust methods like bootstrapping. And the textbook goes into that for some of the parametric tests. It gets kind of harder and harder to do bootstrapping. I think you can bootstrap. I think you can bootstrap confidence intervals in SPSS, and then later on, it's like, oh, if you do bootstrapping for an ANOVA, it says, well, try this code in R. So it kind of gets complicated quickly. Other things, sometimes you might exclude bizarre participants, and that's a bit of a, I don't know if that's safe to you or not. An example I can think of is startle reaction time research. So we have you do a reaction time task, and as you're about to go, we startle you, usually with a very loud tone. And that research, typically 50% of the participants are excluded because they don't startle. And then when I read that research, I always think, well, how much does this tell me? Does this tell me about half of the population because it only applies to half the people? And whenever you exclude some, there's very strict rules about reporting that in your manuscript. You can't pick and choose and then not say that. Trimming the data, transforming the data, it really depends on your discipline and what's accepted. And even if I think about reaction time, even what's accepted now kind of changes. Every decade there's a different opinion on that for a different popular group. Normality. We looked at this a lot last time, so we want to see that both groups are normally distributed. So we can look at histograms, we can measure normality, at least the skew and the kurtosis, and then we can run the KS and SW tests. The challenge is, of course, is that those tests can either be overpowered or underpowered. So sometimes they give you a clear conclusion, and then sometimes, as you saw in the assignment, it could be one of two conclusions. Oh, I think I have a good summary slide here, yeah. So here we have our histograms. We see our skew and our kurtosis. So our values are close to zero. The skew for the no float group is higher. And if we look at our statistical test, though, we see that they're all non-significant, but because we only have 12 participants, if I'm remembering correctly, these tests are underpowered. So it could be, and there's one of two conclusions here, that our data are normally distributed, or they could not be normally distributed, but we didn't see it because the tests are underpowered. Yes, here we go. So that that's the potential two conclusions in this specific case. Okay, any questions about the three assumptions that we've already seen? All right, so let's look at independence and equal variance. Independence, being independent, is kind of what we saw earlier, where you've got different participants in the two groups. Those participants are independent of each other. So if you had one participant in both groups, then not all of your data would be independent. That would be a problem. You should probably drop, that participant and state as such in your manuscript. Now, the observation within each group should be independent as well. And an example of that is, let's say I'm a participant in the study, and I do it. I'm like, oh, that was interesting. And then let's say there was some deception involved in the study. Again, you let me know about the deception, and now I know the secret. Well, if I go and tell one of my friends the secret deception that's vital for the study, and then they go do the study, then all of a sudden their observations would be independent because they'd be biased by me telling them about it. So that's a more subtle type of independence that can be more difficult to control. So, it's pretty easy to make sure you've got different participants in your two groups. But then you want to make sure that somehow those people aren't biasing each other. All right, last one is equal variance. And this one is kind of like testing for normality, where we're going to see tests that allow us to do this. And again, the tests are not perfect. So equal variance, you may have heard of it called homogeneity of variance before, but it's that each group has the same or comparable variance. So if we look at our data here, I think I reported standard deviation before, but if you square that, you'll get your variance. And the variance of the no flow group is higher than the flow group, but is it significantly different? Well, I don't know. Just looking at them, we need to run a test on this. The great thing about this is you don't have to worry about equal variance if your groups have the same number of participants. That assumption magically goes away if your groups are the same size. And that's one of the reasons, we'll see this again in some other ANOVAs as well. And that's why in research we always kind of want the same number of participants in each group. But then you don't even have to worry about this. So here, we don't need to test it because both groups have 12 participants. But let's say they didn't have the same number of participants. The test we use for identifying unequal variance is called Levine's test. So let's run this on our data. And the individual steps are in the slides here. We're going to go to explore, which we've used before. Say, hey, we want to look at mischief. Yeah. And then we want to separate it into cloak and not cloak. And I think it's in plots. Yeah. So here, if you see this box here, it says spread versus level with Levine test. That's what we want, Levine's test. And I don't know exactly why, but the option you click here is power estimation. Continue. Okay, here. That's best us to think about it for a moment. There we go. Don't know why it took so long. Let's see. Here we go. Here are the results in that box, and I'll just bring it into PowerPoint so we can zoom in on it. So it gives us a few things, but it suggested that we look at the results of Levine's test based on our means or our medians. I can look at both of those, so that's why I've highlighted them. And it gives you the test statistic, the number of degrees of freedom, but what we care most about is the p-value. And just like KS, SW test, a significant p-value indicates unequal variance. So significance is bad, if you will, in this case. It violated an assumption. So here, these p-values are greater than 0.05. So it's suggesting that we have equal variance. Testing this was unnecessary for this data set because we do have the same number of participants in both our groups. But I did want to go through that so you know how it works. So Levine's test, like the tests for normality, they have the same problem. They're overpowered for large samples and underpowered for small samples. And here I have, okay. So let's say we had unequal group sizes and we violated the assumption of equal variance. What do you do? The good news is that the solution is very easy to baked right into SPSS. What we do is instead of assuming equal variances, we don't assume equal variances, or we assume unequal variances. And what that is going to do is it changes your degrees of freedom. The t-value will be the same, but because your degrees of freedom have changed, your p-value will also change. Here, it's changed by so little that it doesn't make any difference in 3 decimal places, and that can happen. So what you would do is you would report equal variance is not assumed with your degrees of freedom to 2 decimal places, same t-value here. And then in this case, when we round the t-values to 2 decimal places, it looks the same, but it will have changed a tiny bit. So I quite like that. You can see that already in SPSS. So if you do violate the assumption of equal variance, just drop down a line in the results. Let's confirm that the p-values did change, but by a very small amount. Okay, let's see here. So this is 0.1000686, and this one is 0.100985. So it's going to be, the degrees of freedom are going to be smaller, and the p-value will be larger. But here you can see, because these degrees of freedom are very similar, there's not going to be very much change to your p-value. So here's our summary slide of what to do with testing equal variance. So this is kind of best case. You have equal numbers of participants in your 2 groups. You don't even have to test it. We can just assume equal variance. Now, if you have unequal participants, if you want to make it as simple as always doing something else, what you can do is just always assume unequal variance. Don't even run Levine's test because maybe it's underpowered, maybe it's overpowered. Just always assume unequal variance. That's completely okay if you want to do that. Now, when you use the assumption of unequal variance, the power of your test decreases a little bit. And if you don't want to get to your power, then you can go a step further and say, okay, well, should I, or do I have to, or do I not have to run Levine's test? So if Levine's test is significant with a small sample size, then you must use equal variance as not assumed. So if it's significant with a small sample size when it's underpowered, that means you have definitely have violated the assumption of equal variance. Now, if Levine's test is not significant with a large sample size, then again, because it's overpowered and still not significant, you definitely haven't violated equal variance, so you should use equal variance as assumed. So if you want, you can just equal ends, always equal variance, unequal ends. You can always use unequal variance, but if you want to look at it a little closer, depending on your sample sizes, you don't necessarily have to. On the assignment in class and at home, I realized I made it probably a little too difficult because the one group will have 29 participants and one group will have 31. And then, well, so they're not both above 30 and they're not both below 30. So if on the in-class assignment, we should probably just always use equal variance as not assumed. Sorry for doing that. I didn't mean to make it that confusing. So any questions about our assumptions? 3 we've seen before. Independence, well, we just want to make sure that we've got different participants for the most part. And then equal variances, which we don't need to worry about if we have equal number of participants in both groups. That will come up again when we talk about ANOVAs. All right, let's discuss confidence intervals. Just to recall our definitions, the sort of definition is that the confidence interval shows us 95% probability that the population mean, also described as mu, is within the interval. That's not entirely true, but the exact definition is if you took repeated samples and constructed 95% confidence intervals for each sample, then 95% of them would contain the population mean. So to calculate confidence intervals for, say, our two groups, we use the same formula that we did with, say, correlation data. We need to know the mean of the group. We're going to plus or minus, we're going to multiply the t-value based on the degrees of freedom of the individual group. So in the Harry Potter example, there were 12 participants, so the degrees of freedom is 11. So we look at the t-value based on 11 participants and 95% confidence interval. And we multiply that by either the standard error or the standard deviation divided by the number of the square root of the number of participants, which is also the formula for standard error. Now, with confidence intervals, there's a few things you can kind of choose what you want to report. You might report the means of 95% confidence intervals of both groups. So we'd say, okay, this is close and this is no close. Or you might report the mean difference. Just if you took these two and subtracted them, what does the confidence interval of the mean difference look like? And some people might even report both. So let's look at those. At least we'll look at A and B. So if we want to calculate our confidence intervals, we can use the data from this table we saw earlier. So we have our means, put in our standard errors. Now the t-value is going to be 11 degrees of freedom. It's not going to be 22. It's not the same as the t-test. So we'll need to look that up. Let's see, 11 participants and 95% confidence interval, so 5% across two tails, and our t-value is 2.201. We can put that in, do a little bit of math, and we have our two confidence intervals. Now let's plot those. And SPSS, we could ask it to plot them, but I think I've done this in either MATLAB or Excel. Looks rather MATLAB. So there are our means shown by the height of the bars, and then here are the confidence intervals for those two groups. So has anyone heard of the rule of I before for looking at error bars for confidence intervals? Well, here it is. So if you have a 95% confidence interval, which is kind of the most common confidence interval to report, then we know there's a significant difference when the proportion of overlap of those two confidence intervals is about 0.5 or less. Let me draw out what I mean by that. So if we look at one confidence interval, just the top part of one, and then we look how much does that overlap with the bottom part of the other confidence interval. Well, the overlap would go from there to there, and we want to see, okay, is this 0.5 or less? No, it's not. It's almost completely overlapping, right? There's like maybe 10% that doesn't overlap. So because these two confidence intervals overlap almost entirely, we didn't even actually need to run the t-test. We could guess that they're not going to be significantly different. I'll show you an example of when it is 0.5 overlap and you then get a p-value of about 0.05. So that's shown here, where I just adjusted the data. And if we look at the overlap between these confidence intervals, oops. So here, how much overlap is there between the bottom of this one and the top of this one? Well, this one overlaps about, well, actually, maybe a little more than 50% of that one. And that's when you'll get a, in this case, I worked it, so we got a p-value of exactly 0.05. And if they're even further apart, they'll still be significant, and the p-value will be smaller. And here's what that might look like. So now there's no overlap between the top of one confidence interval and the bottom of the other. So just seeing these data plotted like that, if you know those are 95% confidence intervals, you would be able to predict that they're going to be significantly different. And here we actually, the p-value is very small. Now that rule of I never really like, because the 50% overlap always takes me a while to remember. I'm kind of looking at them. What would be nice is if we could say that, hey, if one confidence interval doesn't contain the mean of the other group, so if it does, they'll be comparable, so anywhere in here. And then if the confidence interval is outside of the mean, then it would be significantly different. We can create that scenario by altering our confidence interval. So it's still a 95% confidence interval if we use a t-value related to 95%, but we call it a difference adjusted confidence interval. And the only thing we've added in here is we're multiplying this is called half width of the confidence interval. We multiply that by the square root of 2. So here's the math behind it. So it's similar to before, but we're adding in the square root of 2. And because that number is larger than 1, it's going to take your confidence interval from before and it's going to get a bit bigger. So difference adjusted confidence intervals are larger than typical confidence intervals. Here I plotted them for our original data. And the rule of I here is easier. It'll be significant when the confidence interval of one group, think about this group, does not contain the mean of the other group. So this confidence interval goes from here to here, the mean of the other group falls within it. So they're not going to be significantly different. Now it's getting close. You know, if this were down here, it would be outside. So the p-value is going to be larger than 0.05, but close to 0.05. And that's what we saw in this case. So yep, it's not significant. And it's a smaller p-value, close to 0.05. If we look at our other two examples, the same two ones from before, so remember this is when p equal 0.05, and you can see that the difference adjusted confidence interval kind of just contains the other mean, so it's kind of right on the threshold. So I wouldn't just do this and not report the result. You should, check, especially on these borderline cases. But often it's easy to tell from the graph whether or not it's significant, because you can see that confidence interval and just barely contains the mean. This is the example where it was significantly different, and now the confidence interval does not contain the mean. And that's why p is less than 0.05. I think these are becoming more common. I like to report them all the time, just because it makes things easier for visual analysis. Now, what if on the assignment you'll need to do this? I guess for the at-home assignment, the in class you just need the numbers, but the at-home assignment will have you graph them. And SPSS likes to graph, normal confidence intervals. You can say, hey, I want it to be 90% or 99%, but it doesn't do a good job at if you want to change the formula by adding in the square root of 2. So what you can do is after you calculate the means and the half widths, you can put those into Excel and ask it to make basically a graph with custom error bars. In that case, it'll plot whatever value you give it. And so there's some slides here that show how to take your data, your means and your half widths. You make your standard plot, and then basically you need to say, hey, we also want error bars. And we don't want typical ones. We want go into the more options. We say, hey, we want custom ones. And it says, okay, sure, tell me, give me any value, and I'll do that. And that's when you give it your half widths. But when you get to the at-home assignment, feel free to to look over these slides if that's a new kind of process for you. And then just as an added example, I went from the default chart to a more publication ready chart, which is unnecessary for the assignment. I'm not grading the quality of your figures, but sometimes I can't help myself make them look pretty. So any questions about our regular confidence intervals or different adjusted confidence intervals? When we get to paired samples t-tests, in the advanced class, we'll talk about correlation and difference adjusted confidence intervals. Because the rules of I don't actually work for dependent samples t-tests unless we make the correlation adjustment. It gets a bit tricky, and that's why we'll be in the advanced topic. So the other confidence interval that sometimes is reported, especially in a meta-analysis, how big is the effect? How big is the difference between two groups in this case? And that would be the mean difference and its associated 95% confidence interval. And the nice thing about it is SPSS actually does report that. So you can get the normal confidence intervals by going to the Explore menu and asking for them. But whenever you ask for a t-test, see, we didn't really talk about this, but there's our mean difference. So that's one group minus the other. There's a difference of negative 1.25 mischievous max. It gives us the standard error of that, and then it combines that with a t-value to calculate the 95% confidence interval of the difference. So some papers might report this. You might prefer to use that, and that option is completely fine. Do I plot this on the next graph? Check here. One more point, but I can't remember if I have a visual with that or not. Okay, well. This confidence interval, we don't need to do a difference adjustment to it, so sometimes that's a good thing about it. I do like that. The bad thing is we lose kind of the confidence intervals of the two groups because we combine them into one. So there's a bit of a trade-off. But when you're looking at this, and you can see it's similar for variance assumed or unassumed, but not identical. This one should be a little bit bigger. So if we're looking at this one here, what you can do, you can tell whether it's significant on whether this interval includes 0. So if it includes 0, your results will be not significant. So does this range contain 0? Yes, it goes from -3 to just above 0, so that contains 0, and that is why it is not significantly different. If it were significantly different, this interval would not contain 0. So maybe it would go from -4 to -2. If that was your difference 95% confidence interval, then you would know just from looking at that it is significantly different. So these are maybe visually easier to interpret because you don't have to look for half overlap, or you don't have to look for any overlap if it's a different suggested confidence interval. Just showing the calculation here, but because MATLAB gives it, SPSS gives it to you, it's not usually necessary. But you can see, does that confidence interval contain 0? Yes, it does. So the two groups are not significant. Oh, it looks like I've done one too many decimal places there on my data. Let's see, we've got effect size, and then just a couple more. One-tailed, two-tailed, and manuscript. So if we think about correlation, the effect size was straightforward in that you could use the correlation coefficient, the R value, or the coefficient of determination, R squared. But the nice thing about R is you got that from the output of running a correlation. With a t-test, the effect size is not built in, we need to calculate one. And we'll look at calculating Cohen's d, or more specifically Cohen's d sub s. And often when people report Cohen's d, they actually mean Cohen's d sub s. But as with math and statistics, it's best to be specific. So differences here is that we're trying to normalize mean difference. If you think back to those of you who are in the advanced class, remember when we normalized the covariance by dividing by the standard deviation? That's what we're going to do again here. We're going to divide the mean difference by the standard deviation to get a unitless estimate of the effect size. The other thing is, if you've done power analysis before or effect sizes for t-tests, you may know that there are too many options. So these are 3 of the most common. Hedges G is actually typically used for meta-analysis. SPSS does use Cohen's d. This is maybe the most common, or currently the most common. And there's actually different versions of these that have slightly different formulas that should be used in different situations, or some people think are better in this situation than others. But we'll look at Cohen's d sub s. So the math for it is simple. And if you are writing a manuscript, I mean, you can just say, hey, I'm using Cohen's d sub s. If you get a question about it, maybe a good citation to go with is this one from Latin. So you take the difference in your means. So if we remember our results, the mean difference was negative 1.25. And that would be the number of mischievous acts. What we want to do to standardize that is we're going to divide by a standard deviation. And remember, standard deviation is in the same units as the mean. So mischievous acts in this case. If we take mischievous acts and divide by mischievous acts, those cancel out and we're left with a unitless number. Although that might sound strange, it's actually good because we want to be able to compare the effect size across experiments and across fields and different approaches. So if we said the effect size was 2 mischievous acts, well, we can only compare that to other studies that measure mischievous acts. But if we can standardize that, we can come up with basic thresholds like we saw Cohen before. 0.1 R was small, 0.3 R was medium, 0.5 R was large. Then we can do the same thing with Cohen's d. So which standard deviation do we want to use? Because we have 2 groups. Well, we want to pool those standard deviations together, and they're going to be weighted based on the number of participants in the 2 groups. So the full formula for the pooled standard deviation is as such. So you see we've got our degrees of freedom on the bottom. The standard deviation, or I guess the variance, because it's squared, is going to be weighted by the number of participants in those groups. And then we take the square root of all of that to return it so that it's on variance, it's back into a pooled standard deviation. I think we'll go through the math here. But the mean difference, remember, was negative 1.25. The pooled standard deviation, this is the one that's always a little harder to get right, because you kind of got to do the order of operations properly here. But both groups have 12 participants. There's our standard deviation. We're going to square it to get variance. Degrees of freedom is the denominator. And we get a pooled standard deviation of 1.787. And in this case, I think this actually works out. Does it work out to the exact midpoint? Maybe not because of the degrees of freedom. But you should get a standard deviation that falls somewhere between your 2 groups. How far depends on the weighting of participants. So we're going to divide that by our mean difference. And in this case, we'll get a Cohen's d sub s of negative 0.7. The sign is not necessarily important. It tells you the direction of the relationship. So that can be important. But when we assess the magnitude, we just look at the absolute value, which is 0.7. Oh, before we get to interpretation of the effect size, when you have equal numbers of participants, which we like because we can avoid the assumption of equal variance or homogeneity of variance. This somewhat complicated formula actually reduces nicely down to this. Oh, and actually, yeah, from here you can see that it's going to be the exact mean or midpoint between our two standard deviations. Here we go. Now here is a measurement of effect size. So we saw this before with correlation coefficient, but every measure of effect size has its own sort of table. Cohen, in his foundational work, kind of had these original 3 measures of effect size: small, medium, large. Saw correlation, but others have kind of added in, very small, very large, and huge. So with an effect size of 1, the mean difference is the same size as the pooled standard deviation. That's right out of the formula. So you can imagine if your effect size, the mean difference is half the size of the variance or the standard deviation, that's going to be harder to see. The larger the mean difference, the smaller the pooled standard deviation, the easier it is to see something or to record something, and hence the larger the effect size. Medium is typically where we say that there's kind of a visible effect size, or it's something that a participant can feel. So when I look at reaction time differences, if a mean difference is about 100, then that is often something participants can feel. They can tell in one condition or another. They're like, oh yeah, I feel slower or I feel faster. So that's probably likely either a medium or large effect size. Then what we want to do is, because effect size wasn't part of the statistical results, we want to add that in. And we just add a comma, d sub s, this part's italicized, and then we'll say what that value is into decimal places. This value is not bound by 1. Remember, the effect size can be infinitely large, right? Huge with a value of 2. So we do want to have a leading 0 on that if it ends up being a small value. Any questions about effect size for t-tests? We will use a different effect size for paired samples t-tests. Still Cohen's D, but then or is it D? Well, I won't guess. It's either Q or Z. I forget. Okay, 2 more things, smaller issues. Well, 1 versus 2-tailed, which I've mentioned a few times, so we should make sure we're all on the same page for that. And then how to report t-tests in a manuscript, which, because they're very straightforward, it's maybe just a touch more description than is required for correlation. So what we typically look at are 2-tailed t-tests. So if we think about mischief and non-mischief, we just wanted to know, was there a difference in mischief? So either it could be that with cloaks, there's more mischief, or with cloaks, there's less mischief. Either way, we would say if it's in that 5% extreme, we would say it's significant. So the other way we call that is a 2-tailed t-test, because we look at the distribution, and if we're in the extreme either one direction or the other, so more mischievous X or fewer mischievous X, we say that there's a significant difference. Now for mischievous X, we might have had a directional hypothesis, or we might have wanted to use a 1-tailed t-test. So we might say, well, it would be weird if we gave people cloaks and they were less mischievous. I guess it could happen, but maybe we have a directional hypothesis. We only want to know, do you make significantly more mischievous acts with a cloak? And that we call a 1-tailed t-test. So keys for 1-tailed t-test is you have to pick which direction you're testing. Are you looking for more mischievous acts or fewer mischievous acts? And that has to be a decision you make before you run your experiment and collect data. So it's an a priori hypothesis. So why might you want to do a 1-tailed t-test? Well, it's because they're more powerful. It's easier to detect a significant difference. So here's our t-distribution. And so if you think about a 2-tailed t-test, that 5% in the extreme we have to split it into two tails. So 2.5 goes here, and 2.5 goes here. So now, if we get a result, right here, it's not significant. Right here, it's not significant, but if it's here or here, we say it's significant. So we kind of have to split where we look for a significant difference because it could be either a positive difference or a negative difference. With a one-tailed t-test, we don't need to hedge our bets. We can say, hey, we want to only look for a difference in, say, a more mischievous acts with close or less mischievous acts with close. So let's say we're going to look at more mischievous acts with invisibility close, because that seems logical. Then instead of splitting 2.5% here and here, you can actually put all 5% in one tail. And that is going to decrease your critical value for t. And now, with the two-tailed t-test, that was not significant. With a one-tailed t-test, it now is significant. So our statistical comparison is more powerful with a one-tailed t-test. This is why it's very important to decide in advance whether you're using one-tailed or two-tailed, because it can look like cheating or p-hacking. Or maybe you run a t-test, two-tailed, your p-value is 0.06, you're like, oh, it's not significant, I want it to be significant. Let's make it a one-tailed t-test. Make it a one-tailed t-test, you actually can, the math where you take your p-value, you divide by 2, so 0.06 becomes 0.03, significant. That's cheating. So what's best to do if you are going to use one-tailed t-test is to pre-register your study, or at least your analysis plan. There are more and more repositories kind of for doing that. Some papers you can officially submit the first part of your paper, like the intro and the method, and then they say once it's approved, they say great, do the rest, and regardless of what happens, we'll accept it. There's not as many journals that do that. What's more common are there's these repositories where you can pre-register your analysis plan, and then when you actually publish your study, you can say, hey, this is what we did. By the way, it was pre-registered, and that's all time-stamped and official, so people can go back and look and say, oh yeah, from the start they were planning to use directional hypotheses and one-tailed t-tests. They're not cheap. There are other dangers associated with one-tailed t-tests. I'm trying to demonstrate that here. This is kind of relevant to some of the research I do. Let's say you have two researchers and they both are testing something similar. The first researcher wants to know, do females have better mental rotation abilities? And what they do is they test females on 7 different tests of mental rotation. These are actually all real tests that are used. And they test females and they test males. And they do one-tailed t-tests and they look for cases where females are significantly better than males. And they find a few significant results. So they do one-tailed t-test and say, yeah, on 2 out of 7 tests, females are better than males. So their conclusion would be that, yes, females have better mental rotation ability. Now let's pretend another experiment has the same data, but they had it the opposite one-directional t-test or directional hypothesis, one-tailed t-test. They want to know, do males have better mental rotation ability? So when they run their test, they find on a different 2 tests that males are better than females. They don't catch the test where females are better than males because they're looking at one-tailed or all directional hypotheses. And they would end up concluding that no, males are better at mental rotation. And although this may seem silly, and of course you're not going to have 2 experimenters with the exact same data, but this does happen in the literature, where when you do a one-tailed t-test, you are unable to find a significant difference in the opposite direction, even if it's ginormous. So when should you use a one-tailed t-test? It's best when these 2 things apply. First, you have a directional hypothesis. If you don't have a directional hypothesis, I don't know why you'd be doing a one-tailed t-test. And then second, and this kind of gets around the spatial issue we just saw, is when a result in the opposite direction is inconsequential, basically when it doesn't matter at all. So in the spatial example, it does matter. If you want to see our males are better, and then on 2 of the tests, females are better, that's important. An example where it doesn't matter, I think this one's from the textbook, is if you're testing a medication. And you want to say, okay, is this migraine drug better than the old drug? So the old one, it's approved, that's the common use for it, that's what everyone uses, but this new one isn't better. So it's only relevant if it's better. If it's worse, or if it's the same, it's not going to become a new drug. So if it turns out the old drug is the same or worse, well, it doesn't matter. The only thing that's relevant is the new drug better. Because if it is, then it can get approved by the FDA. But if it's not better, or if it's worse, well, it doesn't make a difference in that case. It's not going to be approved. So be careful about using one-tailed t-test. There are some kind of sophisticated things you can do in SPSS, but instead of saying, one-tailed, so 100% here, two-tailed, 50-50, you can say, well, I want to do a one-tail, but leave a chance for seeing something huge in the opposite direction. So then you can put 90% here and 10% here. You'll see that in some advanced stats textbooks, but I don't think I've ever seen that in a manuscript. So what do you do if you're doing a one-tailed t-test? Well, unfortunately, in SPSS, you can't say one-tailed. I'm unsure why, but the math is fairly straightforward. Everything stays the same. Your t-value, your Cohen's d sub s. The only thing that changes is your p-value. And you either need to divide it by 2 if the results are in the predicted direction. So, if you kind of got it right, divide your p-value by 2. And if your directional hypothesis was wrong and the results are the opposite of what you predicted, you need to do 1 subtracted by your p-value divided by 2. And the numbers up here are just based on what we saw in the mischievous acts example. Any questions about one-sided t-test? That's very chatty today. All right, last topic. What do you add into your manuscript? Well, you're going to need something in your method section and your results section. Of course, there could be relevant content in the intro and the discussion, but that I'll leave for you to work out with your advisors. So this is one thing, how you could describe the number of mischievous acts of the group without cloaks were compared to the group with cloaks with an independent samples t-test. So it's important to say that we're using t-test and that it's independent samples. To be very clear, I've added in what I'm reporting for effect size. Effect size are reported Cohen's d sub s, and I've even given a reference in case someone's like, oh, what's d sub s? Because unfortunately, there are different ways to refer to the same mathematical calculation. Different researchers kind of argue about what the subscription is here. D sub s is maybe the one winning at this point. And then here, I'm just adding reported values or means and 95% difference adjusted confidence intervals. And someone might say, oh, difference adjusted, I've never heard of that. So this is a good reference for difference adjusted confidence intervals. If you're not using difference adjusted, then you don't need to say that part. Or you might want to say, hey, we're going to report the 95% confidence interval of the mean difference, if that's what you choose to report. So here are the results. And so here, in the text, I put in the confidence intervals. If this is the most important result in your experiment, you might want that to be in a figure. For a t-test, I don't think it's too cumbersome to have that in the text, but when we start to look at factorial ANOVAs, you might not want to report confidence intervals for 12 groups. It's easier to do that in a table or a figure. So the group without cloaks made 3.75 mischievous acts, and the group with cloaks made 5 mischievous acts. The number of mischievous acts by each group, however, were not significantly different. And then I provided statistical support. So t, degrees of freedom, the t-value, the p-value, these are all in 2 decimal places. And then, oh, I forgot something else. Cohen's d sub s. I hit on the other slide, but I forgot it. So that's one way you could report your t-test in the method and results section. Any questions about that? Well, let's take a peek at the in-class assignment. So your data should be on Blackboard for this. There's 4 columns. The first 2 are for the in-class assignment. So they're labeled ICA as an in-class assignment. And the next 2 will be for the at-home assignment. But you're going to look at the assumptions and actually just kind of the new assumptions. On the at-home assignment, I'll probably touch on all the assumptions, but in class, we'll just look at the new ones, specifically homogeneity of variance. And then I'd like you to calculate all 3 types of confidence intervals, the typical ones, the difference adjusted ones. I don't ask for the mean difference, but then I do ask you to apply one of the rules of I. So you could do whichever one you wish if you want to use the rule of I for the typical confidence interval or the rule of I for the difference adjusted ones. And then calculate Cohen's d sub s, and then report the statistical results for the t-test on your data. That seem okay? All right. Need a break? Feel free to take one.